Hello, everyone. I wanted to reintroduce a topic you maybe have seen in the past and maybe you haven't. It's called binomial expansion, and we're going to try to talk about it using Pascal's triangle. Pascal's triangle is this diagram you see on the right here, and the way we generate Pascal's triangle is every row has one additional term. And the way we build each subsequent row is that we put a 1 on the outside terms, and then we add the two terms above to generate the next row. So, for example, if we're trying to add an additional row to Pascal's triangle here, we would get 4 because 1 plus 3 is 4. 3 plus 3 would be 6. And 3 plus 1 would be 4. I know this seems maybe a little intimidating right now, but Pascal's triangle is this kind of cool number array that ends up helping us in a lot of different ways. And the one that I think is most useful for us is with with binomial expansion, right? We're getting into this difference quotient idea, and a lot of the times we will raise x plus h, like you see here, to an exponent, right? Oftentimes second or third degree, but it actually holds no matter what. Let me show you what I mean. So here on the left, I have some binomials, remember two-term polynomials, and they are all raised to a different exponent. So if I were to raise x plus h to the 0 power, I would get 1, because anything to the 0 power is 1. And we can see, let me work through a few of these and we'll find the pattern. If I were to raise x plus h to the first power, I would get 1x plus 1h. If I were to expand x plus h times x plus h, what I'm really doing is distributing, right, x times x times h times x, h times h. And what we're left with is x squared plus 2xh plus h squared. And if we want to be a little bit fancy about it, we can add those ones in. So look what happens. When we look at the coefficients with our expanded binomials, we should find that those coefficients match the row in Pascal's triangle. Right, we have a 1, a 2, and a 1, a 1, a 2, and a 1. So this Pascal's triangle gives me a shortcut to get to some pretty complicated expansions. Right, if I wanted to look at x plus h to the third power, I would have to, multiply this whole thing again times x plus h. Well, Pascal's triangle gives us a way to shortcut right to our coefficients. Our next row in Pascal's triangle, let me grab another color. Our next row here is 1, 3, 3, 1. So in this particular format, we know 1, 3, 3, and 1 will be the coefficients on each of those terms. Well, what are those terms? Well, we have a third degree polynomial. So we know that the first variable is going to be x to the third, and the last variable, h to the third. Now, as we move, the x's will descend, right? X squared, x to the first. And as we move left to right, the h's will ascend. So we have h to the first and h to the second. So we can see here, just with Pascal's triangle, expanding a binomial is doable in a much faster way. If you want to try it and test your work here, try to see if you can expand x plus h to the fourth power. All right, the coefficients we see are over on the right there, 1, 4, 6, 4, 1. If you'd like, pause now. I'm going to work this problem out and then explain how I did it. All right, here is my answer. As you can see here, I'm sorry, I'm kind of cutting over here. Let me erase this bottom row of Pascal's. That bottom row that we found was 1, 4, 6, 4, 1. And you can see those coefficients get plugged directly in here. For the variables, the x's, the first variable we see, goes in descending order from our degree, 4 to 3 to 2 to 1. H does the same thing but opposite, right? 4 on the right, 3, 2, and 1. And in just a quick snap of time, we can expand binomials very quickly.